Hello, welcome to my YouTube channel. Today's video I'm going to show booting DOS 622 on a V30 processor, which is an 8086 clone, if you're not familiar with the V30. Right now I've got it running. Let me just power it down, turn it back on. So while it's loading, it's going to run a little slow. It's the processor speed's right now 5 megahertz, but the bus speed's a little bit slower. The bus is matched to 5 megahertz, but there's wait states built in. So I'll explain the board here once it gets started. Now, if you're familiar with my other projects, this is using the BIOS, the exact same BIOS from my last project. Okay, so it booted up to the C prompt. It's a little far, but that's not what's important. The keyboard does work. Big thing about the keyboard working demonstrates that interrupts are working. I mean, and the system timer is working, but DOS won't boot if the system timer doesn't work. But it's good to know that both the system timer and the keyboard are working. Alright, so let me explain the board. I'll just leave it running, see how stable it is. So if you've watched my last few videos, I've talked about building the bus controller for this, and this is connected to a 8-bit ISA card slot there. And I did have some questions in reference to the 16-bit ISA card slot versus the 8-bit. So yes, the 16-bit is what we should be connecting to, but something that I learned a few years ago when I was trying to design this is that a 16-bit ISA slot is reverse compatible to 8-bit, and it's kind of like default mode is 8-bit. So if I can run this to 8-bit, then I can run it 8 and 16. 16's easy. It's just straight across right from the data bus to the ISA. It's the 8-bit that gets a little more complex because you're trying to read from an 8-bit ROM over into a 16-bit processor. So what I did, if I can get a good angle on this. So this is my PC motherboard here, my PCXT motherboard project. And what I've done is I've removed the processor socket and I put some pin headers, and I left the address latch and the data transceiver off of it. The purpose for this right here is to simplify the board, the breadboard. Otherwise we'd have to breadboard all of this onto the breadboard for the PC to work. So this is providing the ROM, the RAM, the interrupt controller, the system timer, port 61, the DMA controller, which I don't dare play with yet, being 8-bit. It'll work here, but I'll get back to that. Anyway, so keyboard controller, PC speaker. So what I've done is come off of here to provide down to the breadboard what I need. So like the interrupt request, interrupt acknowledge, come off of this board. Hold acknowledge, come off of the board there. I did include the clock up there. Originally I was going to put it on the breadboard, but just wanted to keep things simple. This also helps prevent just the whole board just bugging out. When you have one wire loose that you can't access, it's just terrible. Okay, so let's get back on good angle here. So what we've got going on, and this is very much like my last explanations, course, you're probably not going to read any of the chip numbers, but I've got the processor, and then I've got a counter, and I've got a ROM, and this ROM is used with the counter as the bus controller. And then out here, I've got my address latch, 1, 2, and 3 here. So A0 through 7, A8 through 15, A16 through 19, and bank high enable. And then I have my data transceivers, and one change that I made, so I've got my D8 through D15 and D0 through D7. So I connected these two transceivers exactly to the processor how they're supposed to be. So these are not really part of the bus controller. What it's now providing is it's displaying to the world your address, A0 through 19, and data, D0 through D15. And that way there's no risk of corruption or cross-contamination when you're doing bus cycles and trying to latch an address. It isolates the data and the address separately, and that's probably the right way to do it. So coming down here though, I've got 2 more transceivers and 1 latch. So this is what I've been building in my last project. So I've basically cascaded from one transceiver to the other, from both the low data port and the high data port. And then these bridge, so coming from the data lines on the ISA, it comes to the inputs on both transceivers, as well as the input on the latch. Probably going to touch something here and crash the system. It's still running. And then internally, I've got, so on the output of the latch, I've ribboned it to the output of the transceiver, which goes to the input of the bus controller here. And the bank high is the other transceiver. So through this, it allows to bridge data, the 8-bit data, into either transceiver, high or low, but also to latch the low side. I probably have to watch some of my last videos to get more into depth on that, but a basic 16-bit data read is it's going to output A0, latch the address, then latch the data in the latch, then increment A0 by 1, and read again, and enable the transceiver into the high, the banked high, the data high receiver there. And that's how you'll do a 16-bit read. So the latch is only for doing 16-bit reads, and you only need 1 latch. The only thing I'm missing here for a 16-bit ISA, as far as the transceivers and the bus go, is one more data transceiver. And these are LS245s. So if I have one more, it would come from the output of the high one, and then it would go through to it would connect to the ISA data 8 through 15. And then through manipulating of the bus controller, the logic here, you would do 16-bit, full 16-bit reads. And the way this works, if you haven't seen my other videos, is there's basically like microcode in the ROM. The data is counted up with the counter, so it starts at 0. As it steps through 1, 2, 3, 4, 5, etc., it outputs from the data out to the control signals on the latch, and the transceivers, as well as the read-write pins. Right now I've got 1 ROM. I think I've maxed this out. I don't know if I can get away with 1. I might need 2 for doing a 16-bit ISA. The counter is reset by the address latch. This is running in minimum mode. You might ask, well, why run it in minimum mode? Well, it actually has to do with the DMA controller. The DMA controller puts out a hold and hold acknowledge to take control of the bus. Maximum mode doesn't provide that pin, which means I would have to build into my bus controller a hold and hold acknowledge. And the only advantage to maximum mode is using a math code processor, which I don't use on any of my projects. I've never used one. I've never ran into, at this level of code, I've never needed one. I mean, if you're doing, I think there's some like spreadsheeting software way back that needed it, but there's nothing that I use that need a math code processor. So anyway, that's the basics of how the board's put together. So the next step, as far as ISA connection goes, is definitely adding in the 16-bit, putting in 16-bit memory. Now, on the 16-bit memory, just the RAM will be 16-bit. The ROM I still want to be 8-bit. The reason being is you don't want to have to split your ROM file odd and even into two different chips. You could, but if you look at any modern PC, that's not how they do it. There's a chip 1 and a chip 2. There's always just one ROM chip. Well, your really modern computers, yeah, you're not going to have a big chip like that. It's going to be something different. But the generation of a little bit ago still had chips like that. So add in also a second interrupt controller, because the 16, you might as well take advantage of the whole 16-bit ISA. So second interrupt controller, and then a second DMA controller. And I need to figure out how to implement the interrupt controller will be easy, the DMA will be a little more difficult. So the one thing is, we could leave a single DMA controller, but with 16-bit RAM, it'd have to be 16-bit sometime and 8-bit other time. It could get as complicated as this bus controller. So let me go through a little bit of code on the computer. Let's see what it'll run. I actually haven't played with this. I was so excited. I just wanted to push out the update. Let's see if we can just bring that closer. Oh, perfect. And let's see if it's still actually, oh good, we didn't crash it. So the system's running pretty sturdy right now. Let's go MS, let's see, do I have check it on here? No, I don't. That's what I should have got, is I should have made sure I had check it on there. Oh, the camera's jumping all over. MSD is not quite the same as check it, but it'll give us some information. Okay, so it says it's a V20 or V30, which obviously it's detecting. It says it's got some extended memory. That's not true. 512K, yep. No COM ports, no parallel ports. It says we've got an A, B, and C. Not really. It says we've got a game adapter. That's not true. So. Let's see what else we got on here. Let's see how Sopwith plays. This will also demonstrate the sound. Yeah, the sound works. Not very good view on there. Let's just exit the game. I just wanted to see if it would work. So, anyway, this definitely shows that the system is working with a 8-bit ISA. It is a V30. So, anyway, if you have any questions, you can leave a comment or shoot me an email. Thanks for checking out the video.